those back in at the end. Okay, shall we try one? It seems kind of big and scary at first, and the first example that we'll do will take 15 or maybe even 20 minutes to go through. But that's by far the longest and slowest that we'll do it. After you've done a few of them, you can really pretty much zip through them. Now, there are a lot of steps, and each individual step is pretty easy, but there's so many steps, it's easy to make a mistake, too. So just try to be very systematic about it and careful. And we should be fine. Everybody good with this slide? Okay. So here it is. You need to be told what the environment of the reaction is. It needs to tell you whether it's in an acid or a base. If it doesn't, then feel free to ask, because you need to know that. Notice this is in Chapter 18, not in Chapter 4. Chapter 4 doesn't really show us the Chapter 4 does not show us the half reaction method. But Mr. Hevel and I both feel like, yeah, we need to at least show it now. And then you'll have the method. They show a simplistic method in Chapter 4 of the book. And sometimes it works, but other times it doesn't. So we just want to go for the gusto. So when you have this thing to balance, and we've decided you can't balance it conventionally or by inspection because you have the absence of the O's on the one side. So that means we're stuck balancing using the half reaction method. And in the half reaction method, we're going to, over in the margin, give ourselves an ox and a red, oxidation and reduction. And then when we start this thing, we're going to actually write the half reactions right in the middle of the page, because we will need to add things to both sides, the left and the right. So that's what we're going to make this look like. Before we do anything else, though, can we be sure that this is a redox reaction? Now, I understand that it says the word redox up at the top of the slide, so I'll give you that. But can we trust that? Is it really a redox reaction? Well, the only way that we can know is to know what the oxidation numbers of the reactants and products are. If oxidation numbers change, then yes, it's redox. Otherwise, I don't know. So let's do that first. Let's come up with what the oxidation numbers of everything are. This is the rules that we learned on Friday. We have bromide ion, Br with a -1. Bromine is considered a monatomic ion. What's its oxidation number? It's just -1. Yeah. Whatever the charge of a monatomic ion is, that's what its oxidation number is. Okay, and then when you have the permanganate ion, MnO4 with a -1, we know that the oxygen is going to be a -2. So what does the Mn's oxidation number have to be? What is it? 7. Right. I may have heard a 6 in there. It's a 7. The whole thing has a -1 charge. So the 4 O's make up a -8. So what plus -8 equals -1? It is a positive 7. And then over here, the bromine. Bromine is a diatomic neutral atom. It doesn't matter that it's diatomic. All neutral elements are going to have an oxidation number of 0. And then the next one, the manganese ion, it's got the oxidation number equal to whatever its charge is. So I ask you again, is this an oxidation-reduction reaction? Yes, because numbers are changing. Who gets oxidized in this reaction? The one that gets oxidized has its oxidation number go up. Who goes up? The bromine does, yeah. It's fine that it started as a negative. It went from negative up to 0. So the bromine oxidizes. Now what I like to do, I'm going to show you by modeling this. It may sound corny or maybe elementary, but I would suggest that you, if you have them, take out like 4 or 5 different colors of pen, or even more, and every step use a different color to do. Because when you go back and look at it, it's very easy to follow what your steps were if you use different colors for it. If it's all the same color, you go back like, huh? But if they're in different colors, you can kind of track what you were doing. So you'll see, I only have 4, like I say, but I'll take advantage of that and the fact that I have any different colors at all. So the half reactions look like this. The oxidation half, we decided the bromine oxidizes. When you write the oxidation or the reduction half reaction, you want to include all the, include the entire term that the reacting or produced thing is in. And what I mean by that, it's not real hard to know what the entire term from the bromine is, just Br negative that we start with. And then it changes to Br2. This is what we consider the oxidation half reaction, because the bromide ion became bromine. It oxidized. The reduction half reaction was the Mn as a positive 7 changing to positive 2. The oxidation number of the Mn went down. So I just mentioned before, we need to include the entire term. Don't just put Mn plus 7 yields Mn plus 2. The permanganate was, the manganese was in the form of permanganate. So in the reduction half reaction, we can't suddenly break those bonds. We have to keep the permanganate together. And that changes to what it is over there, which is just Mn plus 2. And it's fine. We'll take care of that when we balance the half reactions. That's what we start with for half reactions. We have what oxidized and what reduced. Just treating them separately, even though in reality they depend on each other. That's where we got the term agent from. Okay, so now I have my half reactions written. I put that marker down. I'm going to pick a different marker up and do the first step. First step was writing the half reactions. Second step is balancing all the atoms other than H's and O's. Now in the oxidation half reaction, I got 1 bromine on the left and 2 bromines on the right. So I do have something that I have to balance there. Take care of the bromines, they're not H's or O's. In the reduction half reaction, I have 1 manganese on the left and 1 manganese on the right, so that's fine. I don't have to do anything with it. So I'll set that marker down. I got number 2 taken out. Go on to number 3, step 3. We're going to balance the oxygens, if they're present, by using water molecules. Now there's no oxygens up here, so I don't need to add any water molecules. But down here, that's the rub. You know, we were looking at this thing at the beginning, before there's any writing, clicking. How can there be oxygens there but not there? Well, yeah, they had to go somewhere. Where they go to is, they do break off of the manganese, and they react with some hydrogens and make water. So there were 4 there. We need to make 4 water molecules at the end. That takes care of the oxygens. There were no oxygens in the oxidation half. The bottom half for the reduction, 4 oxygens, so that's all set. I'll put that marker down. And in the new color, we'll balance the hydrogens. Now again, I don't have to worry about the hydrogens up in this oxidation half, but I do down in this half. There's no hydrogens on the left, but there's 8 hydrogens on the right. So if I got 8 hydrogens that I made, I need to have started with 8 hydrogens. That's why we write these off to the side and leave space, because we will have to write things on the left. So now at this point, we have everything balanced in terms of atoms. all the atoms are balanced on both sides of the arrow in both half reactions. The only thing that's not balanced, though, is the charges. And it's pretty easy to see in the oxidation half reaction. You have a total of -2 on the left, but the right side is 0. And what we do when we have the whole reason for splitting these two half reactions apart from each other is to get both half reactions to balance out. Now, it's only balanced for atoms, not for charge. It's got to be balanced for both. So now I'm picking up a different color. Unfortunately, I need to revert back to black. The oxidation, the definition of oxidation is the loss of electrons. You're always going to give off electrons in the oxidation. I'm going to have to fill something into that blank in a moment, but I just know that there's going to be electrons given off in the oxidation. There has to be. That's what oxidation is. It's the loss of electrons. The reduction half, reduction is the gain of electrons. So they'll definitely go on the left side. Okay, now how many electrons? If I start with a -2, I need to end with a -2. And when I say that when the charges need to be the same on both sides of the arrow. So we need to fill something into that line there to say how many electrons we need. If I started at a -2 here, then I need 2 electrons to get the right side charge to equal the left side's charge. And that's what happens when you have 2 bromide ions and they become Br2. Each one has to get rid of an electron, so we have 2 electrons there. And what happens to those 2 electrons? Well, that was the oxidation process. The thing that reduces grabs onto them and undergoes this reaction. Now, how many electrons will we need to take in the reduction? I always do this. Whatever side the electrons are on, I look at the other side. So in this case, I'm going to look at this side. The water's neutral, but this is +2. So I'm going to have to add electrons to the left to get the left side down to +2. Now, covering this part up, what is the charge right now of the left side? It's +7. Yeah, you got a +8 there and a -1, so overall that's a +7. If that side's +2 and this side is +7, they need to be equal to each other. How many electrons do I need to add to this side? 5. To get this side, that +7, to get it down to +2, I need 5 electrons. So now, the left side is +2, the right side is +2. The atoms are balanced on both sides. So we have 2 half reactions that are completely balanced. Now, we would hope to be able to add these 2 half reactions back together and get an overall balanced net ionic equation. There's one other step, though, if you just take a look. I believe we're on now step number 6. Yes, step number 6. Step number 6 says this. If this half reaction gives off 2 electrons, how can this half reaction take in 5? They need to be the same number. Your number of electrons given off must equal the number of electrons taken in. So that means that we're going to need to use a multiple, in this case a multiple of both. When you give off 2 and you take in 5, we'll need the lowest common multiple between 2 and 5, 10. So that means this, taking a different color, I'm going to take the that oxidation half reaction and multiply through by 5. This entire step is just to get that number equal to that number. Because that's the whole idea of a redox reaction, is somebody needs to get rid of electrons, somebody needs to take electrons, but those numbers have to be the same. The reduction half, in order to get 10 electrons, I have to multiply that through by 2. So I'm going to rewrite these 2 half reactions now, balanced, with their multiplier underneath. In a different color, here it comes. The oxidation half is going to look like this. Distributing that 5 to everything is going to be 10 bromides. And when you're rewriting these things, keep the charges. Don't just put 10 Br. You'll be sorry. So include charges. 10 bromide yields 5 Br2s and 10 electrons. The reduction half reaction, we're going to distribute a 2 through that whole thing, so it's going to be 10 electrons and 16 hydrogens And if you think 16 does a lot, just wait. Sometimes we'll be in the 30s or even higher.